Today's lecture is about syntax and meaning. So, in all of what we've done so far, we've been writing programming languages, either IM or LAM, and we're writing about the syntax of them. We gave you a syntax for the programs themselves, we gave you syntax for environments, we gave you syntax for values, we gave you syntax for reduction, big step, reduction, judgments, we gave you syntax for small step, reduction semantics, we gave you syntax for types, we've given you syntax for typing judgments. Everything has been syntax. And syntax is what you write down. Right? They're the scrawls you make on the piece of paper. So that's what syntax is. Scrawls on bits of paper. Of course, you know, I choose that to sort of give you an idea that it's handwriting. It's something we do. And the grammar is trying to tell you what is a good scrawl, you know. And the type judgments are trying to tell you what are good things. What are good things to write down? But these are things we write down. But actually, here's a question. Does any of what we write down mean anything? So this is meaning. I shouldn't write down. In particular, real world meaning. So, I mean, these programs, which are just pieces of syntax, providing you've used the grammar correctly, and maybe they have typing judgments, like we've just done, they're programs, right? But what do they mean? So we have this idea in our head that a program computes something. If you give it some input, you get some output. So there's some idea of some meaning inside there, and we've never talked about meaning. So far, all we've done is syntax and judgments. And some people believe that that is all that there is to do for meaning, but not everyone. And if you like, this is essentially language. Things we say, or things we write. And I want to focus again on this is the real world. So, a little bit of history. For 3,000 years, this is my opinion, by the way. In other words, we use language to think about the real world. The real world exists first, and then we use language, secondly, to think about it. You know, we look at the fields out there, you know, and they say, I wonder how much corn we can plant. It has a certain area, and we use our language to describe that field and to be able to reason about the real world. So this is like, you know, physics and chemistry and engineering, etc. I mean, engineers, they're interested in bridges, you know, and they use their language to describe the bridges. What? Is this, aren't they interested in bridges?
Yes. To the exclusion of everything else.
Well, everything's a bridge if you look at it abstractly enough. Now, what I want to point out to you is computer science is very revolutionary. The language comes first, and then the real world comes afterwards. In other words, our syntax is all we need. It doesn't necessarily have to model anything. You know, it is just defined completely formally by the grammar rules and the typing judgments I've given you. So there's our programming languages, and we can execute them. And it doesn't matter how often the sun comes up, and it doesn't matter anything about the real world. They're properly formally defined mathematical objects. They're rigorous. They're precise. So they can exist first. And then what we can do is we can use the real world to check that our grammar and our language is reasonable. So this is complete heresy. Language first, and then we use the real world to check that our language makes some kind of sense. And this is kind of what we're going to do today. So we're going to look at the real world and use that to interpret our language. So I think this is fascinating, which is why I spent 5 minutes talking about it. I hope you think it's fascinating. You know, it's a really fundamental question. You know, does the world exist and we use language to talk about the world? Or do we have language And it is our language which creates the world in front of us. You know, if I was blind, then sight is a kind of language. If I was blind, I couldn't see the real world. So my world would be very different from other people's. That's a very modern idea. I think it's very good. And computer science at the forefront of it because we study language. Now, what does that mean to you? It means the following. That's a bit see-through. It means concretely the following. So there's our syntax. A program has a certain type in a certain context. So what should the meaning be? Well, the meaning, it should be something like, this is a program. It takes some input and returns some other output. And in terms of what is that input? What is that output? What do these things mean? Well, if you want to be rigorous, the world of meaning is the mathematical world. So it should mean T represents a function that takes as input something in the set gamma and returns something in the set sigma. So it might seem very similar. I mean, this thing could look like this. Often I'd say, well, T is something, it takes something from gamma as input and returns something of sigma as output. But the thing it takes in is, well, it takes in things which have type sigma and returns things which have type gamma and returns things which have type sigma. But here, you see, I've written the word set. So somebody, a few lectures ago, said, what's the difference between this symbol and this symbol? And this is exactly the difference. This symbol talks about the world of sets and functions, whereas this symbol talks about the world of types and terms. And they're different. And you know they're different because you've got different words for them. One's called term and type, one's called set and function. So what we're going to do is do a kind of translation. Okay. Now, because we're going to translate these things in, T, it can't actually be a function because T is a term. So we write little square brackets around them. So that should have like that. And gamma can't be a set because it's a context. And sigma can't be a set, so we're going to put square brackets. And that's what we're going to do. I've told you the program now, that's what we're going to do. We're going to translate our world of language and programs into the mathematical world of sets and functions. And we know lots and lots and lots of things about the world of sets and functions. People have been studying mathematics for, guess what, 3,000 years. So that's why we want to do this, because we can reason about our programs by reasoning about their meaning. So how do we do that? So this is the goal. What's the time? 12:30. Okay. So if we're going to do this goal, that means we have to turn types into things. We're going to have to turn contexts into things. And we're going to have to turn typing judgments into things. So we've got three things to do. We've got three sorts of bits of grammar. We've got to translate them all. Right. Okay, so types will be turned into sets, contexts will be turned into sets, and typing judgments, in other words terms, will be turned into functions. That's what we're going to do. Okay, so first of all, turning types into sets. Okay, well this is not so hard. We know our types come in two forms. So one thing is the type of natural numbers. So what is the set representing the type of natural numbers? You won't be astounded to know it's actually the set of natural numbers. Now again, this is where you have to make sure you check you know what everything is, because remember that is the type, and then this is the set of natural numbers. We could use different symbols, but then they're so intimately linked, we say, okay, let's use the same symbol because it helps our memory. Just like when we do plus, we have plus in the syntax, we also have plus for adding numbers, and we just use the same symbol. If you're new, if you're a novice, this can cause you confusion, which is why I remind you of this regularly. But eventually, you'll thank me for it, because you don't have to invent new symbols. Okay, so that's the type that is going to be the natural numbers, and the only other type are function types. Remember, a function type looks like this, where sigma is a type and tau is a type. So, what is that set? Well, I'm going to tell you. Let's just say it's a set of functions. So it's a set of functions from the set representing sigma to the set representing tau. So, in words, slightly imprecisely, but easier for meaning, what this says is the set representing the type sigma arrow tau is the set of functions from the set representing sigma to the set representing tau. So you know it's this because it says the set of functions, that's what that's doing, from the set representing sigma to the set representing tau. So now I've told you inside your programming language, here it's Lamb, all the types, they represent sets. And since types are of these two forms, this is sufficient to do that. Everyone happy? Any questions? Any confusion?
A lot.
Pick one of them. And I'll try and help.
Everything.
Everything is such a depressing and distressing answer because I don't know where to begin. I mean, do you remember that in the first year you did something on sets? So you know what sets are? Yeah? You remember what sets are?
Yeah.
Okay, good. So you know what the set of functions is between two sets. So hopefully this makes sense, and this makes sense. So all I'm just doing is turning types into sets. Is that by itself?
I think the confusion's coming from the completers more than anything.
Oh, I see.
I'll get there.
Right, you know what? I'm going to try and do something amazingly difficult. I'm going to try to stop using Greek and start using... Yeah, who's that? Are they Indians or are they Romans or Greek? No, who used... Where does our alphabet come from?
The Latin alphabet?
Pardon?
The Latin alphabet.
Latin. Okay, I'm going to try and use Latin in case that's better. So, okay. So, if A is a type and B is a type, the set representing the type A arrow B is the set of functions from the set representing the type A to the set representing the type B. Does that help?
Yes.
It does?
A lot.
Okay, right. So instruction to everyone, if I slip into Greek, remind me, go Roman, go Latin. Yay. I mean, you have to tell me this, you see, otherwise I don't know how to do it. It might be obvious to you, but it's not obvious to me. That's why teaching is something we do together. All right. So I've explained how to turn types into sets. So the next thing I have to do, if you remember, our language is very simple, is I have to turn contexts into sets. Okay? So now I need a new letter. So if you remember the definition of turning contexts into sets. So if you remember the definition of contexts we defined to be either empty or a context and a variable equals, no, has type, sorry, and a type. And I'm going to remember that I promised to use Latin. So that was what we said contexts were. So I'm going to have to turn all of those contexts into sets. Okay, so that means I need to write, so that's an empty context. So a context, and I need a letter for gamma.
G.
G, I guess the G. Huh?
I think there's only one choice for that, right?
Yeah, except G looks like A, whereas this is a context, that's a type anyway. Okay, so there's a context, G, and then comma, and then X, colon, A, and A is a type. So that's another type of context. So I've got to turn these contexts into sets, I'm going to turn these contexts into sets. All right. Well, if you've got the empty context, I need to give you a set. Oh no, I've drawn my shirt. Bloody hell. In biro as well. Anyway. Right, so there's not too many choices you could write for the set here. There aren't many sets you know about. And the empty context is not going to be the natural numbers because it's empty. The natural numbers, there's something else. You might think it's the empty set. That's a set. But actually it's not the empty set, and we'll see why in a minute. It's the one element set. So I'm going to write 1. So this is the one element set. If you really want me to tell you which element it is, it could be anything, it doesn't really matter, but typically we write star or asterisk. But it doesn't matter, it's a one element set. Okay, so I've told you which set models the empty context. So now I have to tell you which set models this context. Well, remember, in a sense, this is giving meaning for the context G and meaning for the type A. So something in this set should be something for G and something for A. So it's a Cartesian product of sets. It's the times. So it's whatever the set G is times, and we're defining what the meaning of a context is, so that's fine. This is a recursive definition. I'm saying what the meaning of a context is, and I'm using the meaning of a smaller context. So I'm using recursion, that's fine. And times the meaning of A, or type A. And since A is a type, I've already told you what they are here. I've already given you the meaning of types here. Okay, so when you get the hang of it, not much to write. I said I have to do 3 things. I've already done 2 of them. I've told you what the meaning of types are, and I've told you what the meaning of contexts are. What set each context is represented by. So I have to check, is everyone happy by the Cartesian product of sets? Yeah?
So like that's times not the same x that code.
Ah, right. Yes.
It is very confusing afterwards
Yes.
when you read your notes.
You're right. Typical, I can try and get away from Greek, but you're right. We have the symbol times, and we have the letter x. X is our favorite variable name. Times is, so, yes. This is, just to be clear, this is the Cartesian product of sets, which you've done before. And I will remind you of anyway, in case you've forgotten. I know you won't have forgotten, because you've absorbed every single thing we've told you, but I'll remind you. But you know it really can't be x, because what does set, little variable called x, and another set mean? It wouldn't mean anything. So it can't really be little x. But what it means is the Cartesian product of sets. And what is the Cartesian product of sets? Well, that's the same thing as it's pairs of elements, if you remember, where the first element is from the first set and the second element is from the second set. So that's what this is. This product, it's a set and it contains elements. And the elements look like pairs of things. The first thing comes from the first set and the second thing comes from the second set. I think you did that in your first year. Well, I know you did that in your first year. Okay, brilliant. I've done contexts. So now all I need to do is tell you how to translate terms to functions. Now, well, there were two types and two functions, so we have two clauses. There are 5 sorts of terms: applications, abstractions, variables, additions, and numbers. So we're going to have 5 rules, one for each of them. Oh. Ah. Oops. So the last thing I have to tell you to do is how do you turn these typing judgments into functions? So in other words, given a typing judgment, which now looks like this, I'm going to have to turn that into a function. So I'll write it like this. And it'll be a function, so it has to have, because it's a function, take elements of a set as input and return elements of a set as output. So it takes elements of the set which represents the type G as input and returns elements of the set which represent the type A as output. So, like I say, you know that we often speak of the term T, we think of it as taking things of type G as output, as input, and return things of type A as output. And now we see that really for sure as a proper mathematical function. It takes elements of the set G as input and returns elements of the set G as output. Previously it was just intuition. T was just a term. But now we actually have it as a function. Taking inputs, returning outputs. Okay, so all I have to do is give you the 5 rules. Have we got time for you to do them all? Right. Well, let's see. Shall we start with the natural numbers? So,
what's small n?
Sorry, I wrote G. I wrote gamma. Small n. Well, if you remember, the syntax for lambda calculus says if n is a number, then it's a term. So this n is a number. We know that because we can go back to the grammar defining this language, which says that numbers are expressions. Okay, so this should be something, should be a function. It takes an element of the meaning of G as input, and it returns an element, a natural number, as output. Okay, so we know how to define functions. If you give it some input, I don't really want to use little g. Do you mind if I'm going to use little x, so that's it? Is that okay? Right. Okay. What should this function return? I'm bored of listening to myself. What do you reckon? You've been paying attention intently.
Yeah, I just got lost when the x is supposed to be from the set g.
Yes.
Oh, okay.
And you know this because I've said that this thing is a function. It takes as input an element of this set. So I had to give you that input. So I had to write x. So this is an element of the set g. But it equals, now the output must be an element of the set of natural numbers. So which natural number do you think I should write?
The natural, just a natural number set?
Yes, which one? I have to give you a specific natural number. Shall I write 3 down?
No, just like as number of the, like that's contained in the set.
N. So n is a number. So this might sound trivial, which is great because it means you can do it. This is not magic. In some sense, it is fairly straightforward. It gets more complex with the abstraction, of course, and application. But guess what? The meaning of the number n in this context is a function that takes some input and then it says, well, hey, I'm the natural number n. I don't require input. You can see there's no free variables in n, so you know it's not going to use the input. And I'm just going to return a number. If I'm the number 3, well, I'm going to return 3. If I'm n, I'll return n. Okay? Right. So there's some... So remember, there's a rule which says that S and T can be natural numbers, providing you can show that in the context G, S is a natural number, and in the context G, T is a natural number. So that's one of our typing rules. So now we've got to turn that into a function. So that means that S plus T should be a function that takes an element of G as input and returns an element of N as output. Do you feel at the back I'm neglecting you by starting at the front? Is that yes? Yeah? Okay. I'll take your silence as a yes then. So let's go to the back. Okay. Can we start with you? Hello? Yeah, can we start with you? Can you give him a prod?
I'm kind of lost and sorry.
Okay. Well, if anyone is lost, I kind of wish you'd tell me because I can't help you unless you say so. So this has got to be a function. It's got to take an element of G as input and return an actual number. So how do we say this? What the input would be? Here, this was a function, and to say what it does, we gave it a variable to represent the input. So what do you reckon? Should I do the same again? Yeah? If I'm going to write down a function, I will define it and I'll say, well, this function, it's got to take an element of G as input, so let me give it some input. And then write equals. So all I'm saying is, how do you write down functions? If I say I'm writing down a function that takes something as input and returns something as output, well, I write down the function, I write down some input, I write equals, and then I'll tell you what the output is.
Can you write like A, write I will be or something?
Sorry?
Can you write like A, write I will be and use those as placeholders?
Can I write? I mean, I'm not going to write arrows here. I could write an A here. Is that what you're asking? Okay. So if you send me an email, I'm happy to go over this with you later. What do you think then? What's the next thing I should do?
I thought in general that you needed two variables for input because of S and T, they're obviously different, so shouldn't we give...
Okay, that's a good point. Perhaps S and T are different, I should get two variables. But actually the information is in front of you. This tells you this function takes one input, so one variable. I mean, later on, actually, this set could be a product. You know, we saw we use Cartesian products. So had it been a product, we know we'd be taking 2 inputs. But this tells you shouldn't be doing that. There's 1 input. Now, of course, S can use X, and T can also use X. So you're right, S and T are 2 different things, but they can use the same input. Okay, so that's a very good contribution, so I'll move on. So next, what do you think we can do? What number shall we get, or how shall we get a number? We know we need to get a number because we've got n here. Okay, so we could write, let's write s plus t carefully. Okay, so it's going to be something like that, but it's not quite that. So can you point out what's wrong with that? Yes. So I think what you're telling me, correct me if I'm wrong, is that when you said shape, type, what type are S and T? S is a function. Well, first of all, S is going to require some input, and T is going to require some input. And they've got to be functions. But this S, of course, is just a program. We can't just write plus as a program, because we're trying to get a number. So those are the sorts of things that are mistaken. So how can we rectify it? What do you reckon? What would we do if we want to turn our program S into an actual function? Can I give you a clue? This is the thing that turns types into sets, context into sets, and terms into programs. Terms into functions.
So, do we put brackets around the S and then X?
Wonderful. Sort of. So, yes. So if I write brackets around the S, that is no longer the term S, that's the function that represents the term. So now this S is a proper function. And the typing rule will tell you that S has type, in the context G, S has type N. So that means the function S, so this thing, is a function. It takes an element of the set representing G as input and returns a natural number as output. So it wants some input. And then it'll be a number, and then you can add it. So thanks for that, but I know you're keen, that's very good. But I don't want to deprive you of the opportunity for learning, so your turn next. That S, it's a function. I can't add it. I need to give it some input. What input should I give it? Yes. Very good. So this is S plus T is a function applied to the input X of type G. S also requires something of type G as input. X is the obvious thing to give it. Because S could take 3 variables. So therefore, the elements of the set G are the meanings of those 3 variables, and X is an arbitrary input. Getting close. Your turn next. Yeah. T is a term, but actually we need a function. Good. And one last thing to do. Your turn. Yes. This is a function. We can't add functions together. We can only add numbers together. But if I give it the input X, which has the right type, that's a function. Okay, that's probably a good place to stop. In fact, that's the perfect place to stop. So, guess what? Next lecture, we'll finish off the rules by doing the complex ones. Yeah?
How should we prepare the test?
How should you what?
Prepare the tests on Thursday.
Know the material?
What material specifically?
All the stuff on reduction. So, I can tell you, yes, so the test is solely about the second part of the course. All the stuff on reduction. So there could be stuff on, what was it? The big step semantics for imp, the small step semantics for lamb, and the big step semantics for lamb, as well as the closure semantics and the lazy semantics, the thunk semantics. The other bit we did. Everything I've told you about reducing terms. You've already done the homework, so you know all about it.
They've got their,
Oh, by the way, also, we brought the first hand in, so that should be in your Git repositories. Hi.
Where can I get
Why can you get to what? Oh,